As I mentioned at the end of the last video, the limits that are going to be the most interesting are limits that we can't evaluate by simply plugging in the point that we're approaching. And most often that's going to occur when the point that we're approaching, which in this example here is the origin, is not in the domain of the function. Now, I can see that the origin in 2 space is not in the domain of this function because that would put a 0 in the denominator. Okay, so I can indicate that the denominator would be going to 0. And I can look at what happens on the top. If I did try to plug in 0, 0, that would also make the top go to 0. Now this arrow notation is perfectly acceptable. That says as we get close to this point, the top gets close to 0, the bottom gets close to 0. That is true. Here's what's not true. I'm switching to a sort of reddish marker to indicate that what I'm about to do is bad and wrong and should not be done. Okay, so I am not going to write that this equals 0 over 0. Ugh. Let's cross that off. Let us label that as bad and wrong, for that is a mathematical atrocity. You can't divide by 0. Don't tell me that you can. Do not tell me that anything is ever equal to a fraction with 0 in the denominator. We can't divide by 0. Okay. I am very picky about that. I will take off points every single time you write a 0 in the denominator. Now, for some of you, you may have developed that bad habit of just sloppily writing it down. Okay. Don't. Break yourself of that habit. I am picky about that. Sometimes students don't understand why I'm picky about that. Well, got 2 reasons. One, it's kind of the mathematical equivalent of using good grammar. Okay? You have a brilliant point to make in an essay, you use horrible grammar, you should not expect a good grade. Good grade for the idea, bad grade for the write-up. Bad grade for the write-up. This is bad grammar, called a mathematical atrocity. The second reason is that even though students will tell me, oh, I just meant that informally, I meant this. Well, if you meant that, why didn't you write it? Okay? And I don't believe that you fully understand that you can't divide by 0 if you insist on writing it. And I've seen lots of students who claim, oh, I just meant it informally, I didn't mean anything by it, but it gets them in trouble because there are times when they then do try to divide by 0 in some form or another. So, don't write it. That will help you understand that you can't do it. Okay, so the arrow notation is perfectly acceptable. So we've got this situation now where the top and the bottom both go to 0. And some of you may be thinking, L'Hopital's rule. Stop thinking that too. Okay? Now, I fully understand why you were thinking that. I don't think there was anything wrong with your thought process there, because you were saying, hey, when I have functions of one variable and the top and the bottom go to 0, I use L'Hopital's rule. And there's lots of stuff that works for functions of one variable that generalizes to functions of more than one variable. This is one thing that doesn't. Okay. So, if we were to try to use L'Hopital's rule, we'd need to take the derivative of the top and the bottom. That would be a problem because we haven't yet learned how to take derivatives of functions of more than one variable. So you might think, okay, well that's okay, we'll just wait. In a section or 2, she'll teach us how to take derivatives, and then we can use L'Hopital's rule. Nope. Okay? This is really important. L'Hopital's rule is one of those things that's wonderful and true for functions of one variable, but it is only true for functions of one variable. It does not generalize to higher dimensions. So L'Hopital's rule is only true for functions of one variable. Now, it is true that in a couple of sections I am going to teach you how to take the derivative of a function of 2 variables and 3 variables and all sorts of fun things like that. When we do that, we're going to discover that the derivative is actually a vector. L'Hopital's rule would have me take the derivative of the top and divide by the derivative of the bottom. I can't divide vectors. There's no such operation as vector division. Okay, so it's not going to work. I'll tell you that right now. Okay, so I need to see if there's some other way that I can evaluate this, and there is. I mean, before you learn L'Hopital's rule in 3A, you learn all sorts of techniques for evaluating limits where you do get indeterminate forms like that, and one of them is just to factor and cancel. So I could say this is the limit as xy approaches 0, 0. That top factors as x plus y times x minus y over x minus y. This function is the same as this function wherever they're both defined. So I can say this is going to be the limit as xy approaches 0, 0 of x plus y. Okay. This function is not the same as this function, but their limits are the same. They agree everywhere they're both defined. Okay. And now this function is continuous, so I can evaluate it by plugging in, and so we do just get 0. Okay. So that's one thing that I can look for. Let's take a look at another example. Let's suppose I had the limit as x, y, z, we'll go into a function of 3 variables this time, approaches 1, 2, 3 of e to the x plus y minus z minus 1. So the minus 1 is not part of the exponent. The exponent there is just x plus y minus z, and then over x plus y minus z. Okay. Now, a lot of the problems in the book have you approaching the origin, whether you're in 2 space or 3 space. And that's because a lot of functions, the origin is going to be a problem point. It's the origin that's going to give us 0 in the denominator and cause some problems. And in fact, the origin would be a problem here because it would make the denominator 0 as well. Okay, I'm purposely going to pick numerous examples for us to do that are approaching a different point. And that's just because I think the book overuses the origin, and I've seen a lot of students get to the point where, oh, now I can evaluate this by plugging in, and they just automatically plug in 0 and 0, which of course is not correct if you're approaching the point 1, 2, 3. So I'm purposely going to choose lots of examples where we approach a point other than the origin. Do just be aware, a lot of the homework is going to have you approaching the origin. Don't fall in the trap of thinking that limits can only be done at the origin and that when you're ready to plug in, you're plugging in zeros. Okay. All right, so if I look at this, if I tried to plug in 1, 2, 3, the bottom would go to 0. That's my appropriate way of indicating that. Okay. The numerator, this would become e to the 0, which is 1 minus 1. That would also go to 0. Okay. So we do have this problem that we have an indeterminate form. The top and the bottom are both going to 0. And in this case, I don't see any factoring that's going to help us. Okay. What I do see is that it's the same problematic expression, x plus y minus z, that shows up in both the numerator and the denominator. So what I can do is I can make a substitution. That problem piece, I'm just going to call that u. I'm going to let u equal x plus y minus z. Okay. Now notice, as x, y, z approaches the point 1, 2, 3, u is going to approach 0. Okay. Because if I try to plug in 1, 2, and 3, we just saw, we get 0. Okay. So now I can rewrite this limit having done this substitution. So I can say this is the limit as u approaches 0 of e to the u minus 1 over u. Okay. Now I can use L'Hopital's rule. The top and bottom still go to 0. Okay. And in fact, anytime you do a substitution, if you had an indeterminate form and you do a substitution, you better still have that same indeterminate form. You can't change the fact that the top and bottom are going to 0. If that changes, you somehow did something wrong in your substitution, okay? But now I can say, okay, I've rewritten this thing, but I've rewritten it in terms of one variable. L'Hopital's rule does apply to functions of one variable. So now I'm just going to indicate that I'm using L'Hopital's rule. I usually just put an LH by the equal sign. Now I can say this is the limit as u approaches 0 of the derivative on top would just be e to the u over the derivative on bottom is just 1. That's e to the 0, which is 1. Okay. So it's not that we're going to abandon L'Hopital's rule entirely. It's that we need to be able to do a substitution that converts our limit from dealing with a function of multiple variables to a function of just one variable. If we can do such a substitution, then we can apply L'Hopital's rule to the function of one variable. So that's a really, really useful trick, and we'll take a look at some more of that in the next example.